Welcome to this MIT seminar, given by Professor Kelsen. I'm Paul Skluner from Mechanical Engineering, and I'd like just to introduce the speaker and motivate perhaps the discussion a little bit from my perspective, anticipating what probably we're going to talk about. I'm sure you've all read Professor Kelsen's resume, but he has a PhD from the University of Leuven on flexible multi-body modeling of wind turbines, so he's worked on the engineering structure itself, and presently he's a professor at the University of Brussels. And his group is working on physics-based big data analytics for monitoring rotating machinery, and using these technologies to anticipate failures and optimize the performance of machinery and wind turbines. He has worked closely with the National Renewable Energy Laboratory, and we'll hear more about his research. This is a very important topic in the context of offshore wind farms. The offshore wind energy industry is receiving increased attention worldwide, and one of the primary thrusts of the industry at this point is to reduce costs. One way of reducing costs for large-scale offshore wind turbines is to build them bigger. The bigger turbine on a foundation is marginally more economical as opposed to building more of them on multiple foundations. Takes more trips to maintain, more boats. So the offshore environment is particularly demanding when it comes to O&M. Present cost of offshore wind technology is around 15 to 20 cents per kilowatt hour. We've reached the limit of efficiency from the engineering point of view. We can extract 50% of the available wind energy by designing the large multi-megawatt turbines that are in the 6 to 8 megawatt range optimally. Very hard to get about 50%. If we can reduce O&M, which is 20 to 25%, a few percentage points, that's a big difference. And big data analytics, machine learning, eager to hear what Professor Kelsen is working on, is going to make a difference, and, especially as we move further and further offshore. I probably anticipated your lecture a little bit, but
yeah.
Welcome. And,
thank you very much for the very kind introduction. So I'm Jan Helsen. I'm from Brussels. I'm going to speak about fleet-wide monitoring in offshore. A lot of the concepts that I will discuss are both valid onshore and offshore. We are focusing on the machine itself here. So how can we reduce the costs that are related to maintenance? How can we optimize the design such that we can indeed reduce the total cost of energy of offshore wind? There are three main words in my title. One is monitoring. We try to track what the machine is doing. Then failure prognosis. We try to predict what will happen and try to anticipate already on this and take action in that way. And fleet-wide. We want to go beyond looking at one machine. We really want to understand how are machines in general behaving and what can we learn from this fleet of machines that we cannot learn from a single machine. So I will first introduce some of the initiatives in which we are active and that have helped to gather the results that I'm able to present to you today. And then my talk itself is has 4 parts. So I will first set the scene on offshore energy. So how does it work? What is important there? Why is it done? And then I will move into the cost of energy. As was already mentioned in the introduction, we are still too expensive today. So we need to reduce the costs in order to be viable on the long term. And I will discuss some of the aspects that are important for this. Then I will talk to you about turbine reliability. It's important the machine itself needs to get more reliable or more predictive. I will talk about certain issues that there are and lift out some examples. And then I will focus on the fleet-wide monitoring. What we do in order to try to learn what goes wrong on the machines. And I will end with some conclusions. So first, I will discuss some initiatives which might be also interesting to you that have been going on in the past and are still ongoing and that make this kind of research possible. Maybe something that's important to know is the fact that we only work on real data. We don't do anything on test models. We don't do laboratory testing. We only work in the field on real turbines. And we have had this opportunity due to the Offshore Wind Infrastructure Application Lab. It's an initiative that was started in Flanders in 2010. And why did it start? The fact was we are not that big of a country, Belgium. But we have some high-tech players. And in offshore wind, we were one of the first to actually build a farm. So that gives you an added value or an advantage to the rest. And we had an opportunity in this area, and our government invested. They got the question to invest money in a strategic program to be able to bring offshore to the next level. It was 4 companies who asked for this. GOC, they're a dredging company. They built these palm islands in Dubai, but they also install wind turbines. And they saw a big opportunity for new installation techniques and floating LiDAR. ZF, at the time it was Hansen Transmission, they're building their gearbox builder. They're one of the largest players in the industry, and they wanted to have more advanced testing. 3E, they do resource assessment, and CG is, at the time it was Powell's Transmission, Powell's Transfo. They built transformers and substations. So there was a collective research program started, and it was embedded in the high-tech industry collective center series in Belgium, and the VUB did the scientific coordination. So what was invested in? The first thing is floating LiDAR. I will touch upon this later in the talk. If you want to build a new site, you need to know how much wind there is. If you need to know how much wind there is, you need to measure. Problem is, if you want to measure offshore and you need to install a met mast, it costs a huge amount of money. So in order to overcome this, there was a buoy created that hosts a LiDAR to do 3D measurements, and that can just be placed at any site and do the assessment. Then the second investment was done in monitoring infrastructure and also recently in a big data platform. I won't go into detail here because I will discuss it in the rest of the talk more extensively. So it doesn't I don't go in detail. We focus there on, so for the monitoring, on drivetrain monitoring, everything that rotates, and on foundation monitoring. And then the largest part of the investment went to a climatic chamber. So basically, we wanted to be able to test subcomponents, for example, a gearbox, a transformer, in Arctic conditions and in very hot conditions. So we can go from the North Pole to the Sahara in one day. We can also simulate moist conditions and so on. And this is for robustness testing. The next step in onshore turbines is more towards cold climate. And it's important that you also can test this and learn from this. This is an example where we do a full, where we do a test on a wind turbine converter, wind turbine transformer, sorry. And this is together with CG, for example. So there is, on the one hand, it is used by industry to test products. On the other hand, there is research going on. An example there is that we are active in the IEA Task 19 on cold climate. So that's the first initiative that gave the opportunity to measure offshore and to do monitoring. Then there is the second one. Since 2011, I also work together with NREL, and more specifically with the Gearbox Reliability Collaborative. The Gearbox Reliability Collaborative was established in 2007. It focuses on gearbox. It's in wind. And the reason was that there is failure. Now it's less, but at the time there was a lot of failure with gearboxes, and it was brand unspecific. So the different OEMs were having similar problems, although their quality was very high. So there was the perception that there was something missed in the design. There is something that's not captured in the standards, and there's something that needed to be learned in order to improve design such that you don't get this failure anymore. How this was done is actually very smart. There was a gearbox designed that was completely according to the state of the art. So all the best techniques were used, all of the different players were involved, but it's not a specific one brand gearbox. For example, not a ZF gearbox, it's not a Winergy gearbox, which makes that people can discuss about it. Technically speaking, a lot of people are interested to learn, but it's always difficult if your brand is on there. So that opened the opportunity to talk. who was involved or who is still involved, because this initiative is still ongoing. The different OEMs, so subcomponent OEMs up to turbine manufacturers, owner-operators, the majority of the large owner-operators is in there, academia, and design tool developers. You can see this, it really aims at improving all the steps in the design and really learning. So what is done, there is a large trajectory on simulation, field testing, dynamometer testing at the testing facilities that NREL has, condition monitoring, and a gearbox failure database. Some of these aspects will come later in the talk because I will use some of them in my talk to show certain aspects of what is going wrong. So first, let's set the scene. Offshore. Offshore wind energy has been used already for decades, only in a different way. We've used it already for ships and so on, and today we are at a new chapter. We want to harvest the power of the wind, and we want to do it in order to create electricity. So basically, we want this. You want to have a farm. Offshore, you don't build 2 turbines. You always build 50, 60, 70. So you can really look at this as a convention. It's not a conventional power electricity plant, but it has power that is at least very high. So what I want to discuss is this part of the future? What are the main challenges? And what is the added value of monitoring? Particularly the last one I want to show. I want to show what is the added value of trying to predict what is happening and what you can learn from this about in cost reduction and so on. First, it's a booming industry. Offshore is really getting more and more popular, especially in Europe, and it's continuously growing. What you can also see is Belgium, albeit a very small country, is still a relatively big player in this. So for us, we have the problem, we have no space onshore, almost none. We have a very dense population. So we needed to go into the sea to be able to install these things. The US for the moment is not that big, but it's starting. So it will be very interesting here, particularly because floating will be important here in the US, where it's less important for the moment in Europe. This brings me to my next point. We go deeper and further. Offshore is, the offshore plants are going deeper in sea, where the water depths are a lot deeper. Up till now, we use foundations to install the turbines. So you go to a sandbank where the sea is not that deep. You install the turbine on a foundation. And that way you try to do it at minimal cost. But next decades we will move further into shore, further away from shore, and we will go into floating turbines and deeper water depths. The further you go, the more complex your O&M strategy becomes. If your boat needs to travel for 5 hours to get there, your crew cannot do it. You lose the whole working day just going back and forth. So it means that you will have to have a vessel there, you have to have a permanent installed hotel or something else to host your crew. So this is important. The further you go, the more complex everything becomes. This is to show you Belgium. So we are somewhere in the heart of Europe. We have, for the moment, 4 installed farms, let's say 3, and the last one is under installation for the moment. We have the advantage that we are monitoring on 3 of them. So North Wind, Bell Wind, and Sea Power, we have instrumentation there, and we are monitoring them. So wind as a renewable energy source. We are here at the Energy Initiative, and the primary reason people go for wind is being it a renewable energy source. So the first thing is climate change. Everybody knows this. I just want to touch upon this. There is a tendency to go to renewables for climate change. But there's also other drivers. For example, security of supply. You know that oil, gas is produced, and for Europe at least, we don't have it too much. So we need to import it, and that means that it gets imported through pipelines. Something can happen with it. People can stop it. So you are really dependent. That's why there is an interest to go to an energy source that is less susceptible. For example, wind has the advantage it's produced locally, so it's relatively high security of supply. Then there's the ethical debate. In Europe, it's very much ongoing for the moment, whether or not we should keep are nuclear power plants open. So this is also pushing a bit towards renewables. Renewables is very interesting, also wind is very interesting, but you need to meet demand and supply. So it means that if there is no wind, you still want electricity, so you need some kind of backup. What this backup needs is predictability. It needs to know, okay, we will have this kind of capacity necessary during the year, so we need this and this and this backup because we know that some turbines will be out due to maintenance, some will be out due to no wind, etc. So you need actually predictability. And that's important, as it will come back later in the talk. Then the history of wind. Where I come from, we have a huge amount of these. They're already there for a lot of years. And actually, wind has gone all the way to a very high-tech product, because it's very high-tech industry. But the basic concepts are still the same. We still use a horizontal axis. The turbine is still upwind, so the wind blows to the rotor that is in front of the tower. It means that your blades shouldn't be too flexible, otherwise they hit the tower. You need a yaw mechanism. The yaw is where you rotate the turbine into the wind, such that you can capture a lot of wind. Most of the turbines are pitched today, so it means that they can rotate their blades such that the angle of attack of the blades is as optimal as possible to capture the energy, and when there is too much energy in the wind, to minimize the loads. They're also variable speed, so the time that all turbines were rotating at were driven by this 50 hertz is over. We can now also create reactive power. You can run at multiple speeds. And then there's the debate on whether you should use a gearbox or not. So you have direct drive, and then the ones with gearbox, and a combination of both. It's not decided yet. You have believers, non-believers. It's very interesting because all concepts do have their own issues, and all of them claim to be the best. So I'm very curious to see to what we will evolve. And then we are at $1 million question. It's always the same. I want to go from here to here. It's actually all about the money. It needs to be financially viable in order to survive long term. You can use subsidies or support schemes to support it for some time, but not for a very long time, because it will mean that people will say, okay, no, it's not viable, and it stops. So if you want to survive on the long term, you need to be able to do it without subsidy. So you need to cut all costs that are not necessary and optimize really the behavior of your assets. So let's go through to see what is important and how to do this. Basically, in the end, you want to reduce the capital expenditure, the OPEX, and you want to have yield optimization. We'll go through the blocks one by one and discuss this. So everything starts from the site. You have a mean wind speed at the site. You have a distribution, which you try to assess, for example, with a metmast or with our floating device here. Once you have that, you get a distribution. You know the frequency of the wind at certain speeds throughout the predicted period of 20 years, the one that you will have the operational lifetime of the turbines. And then you choose a turbine that is ideal for your site. There are several things that you choose. One of them is the cut-in speed. At which speed do you want to start producing energy? The cut-out speed. At which speed do you want the turbine to stop because there's too much wind? And then the rated wind speed. What is the wind speed that is occurring the most? And that should be, your turbine should be tailored to that, such that you can harvest the most energy. So this comes down to the definition of the power curve. So power versus wind speed. Then you can calculate your revenue. You know roughly how much wind there is. You know what the turbine can, how much energy it can harvest from the wind, and you know what the kilowatt-hour price is. So you can calculate your revenue. Now we come to the other point that was touched upon in the introduction, upscaling. The bigger I build my turbine, the more energy I can harvest because my blades can grow and I will be at higher wind. And this will have an impact on the foundation and on all other components in the turbine. So there is an optimization on, that you need to do, where you decide on how much energy do I want to take out of the wind, how big does my generator need to be, or my drivetrain, so how much am I willing to invest in my turbine. You can use a big rotor, you can use a small rotor, you can use a big generator, a smaller generator, it's all possible. And it's up to you. So based on what your business case is, you have different brands, different types. It will have an effect on the foundation and all the rest, and on your total cost. But in general, we see that we have been going bigger and bigger. So the past 20 years, there was an increase of a factor of 160 approximately in the size of the turbine. To give you an idea, I've plotted, this is the Airbus A380 next to diameter of the turbine here. It's like spinning this thing around. So it gives you an idea about the size. Advantage offshore is you can go as big as you want. The logistics problems of moving under bridges, moving over roads are gone. Most of the real offshore factories are close to the sea, so you can just come with a barge or with a vessel, take the turbine and go. This factor of 160 is important to put in your minds. It means that in the 80s I was building something they call a 2 chevaux. Today I'm building a Formula 1 car. If you look at the normal evolution of cars, you have a new model every 7 years. So it means that in three turnovers, I've moved from this 2 chevaux to a Formula 1 car. It means that there is a huge amount of technology that needed to change, and that you are getting closer and closer to the limit. You are really becoming less and less conservative. The safety factor that you've used in the beginning, you are not able to use anymore because your turbine will be way too expensive and it won't be viable cost-wise. So it means that there is already huge improvement in design and that there is a lot more known already in this period about how the turbine behaves. But there's still a very long way to go. This brings me to cost. So we've looked at the revenue side. Okay, let's build a very big turbine. Let's harvest all of the energy that's there. Then we come to cost. The first one is CapEx. You need to actually buy the turbine. You need to buy it, and it needs to be as cheap as possible. It needs to be as big as possible and as cheap as possible. On the other hand, it also needs to be as easily installable as possible, because a lot of the cost is in the installation. I will show you this as well. And then with regard to the farm, your substation and the cable is very substantial in cost, so that needs to come down as well. Design as light as possible means be smart. Only use material there where you really, really need it. It means that you need to know what is happening to your turbine, you need to know how design works, and you need to know exactly how to deal with the loads that it is seeing. This has a lot to do with knowledge about the field, and that's coming back later as well. Optimized installation. This thing costs $250,000 a day just to do the installation. You can take the whole turbine, put it on, and install it. The thing comes out of the water in order to be independent of the water conditions. There's a lot of improvement ongoing there. One of the partners in the OELAB project, DEME, have a new installation method where they can install, it's called high wind, where they can install also with high sea and try to go to more robotic installation. So capital expenditure, cheaper turbine by knowing better what happens and more easily installable. Then operational cost. This is the cost that comes back every year. So the other one, you have it in the beginning of the project, you know it in advance. Okay, you finance it, you put it over the different years of the project lifetime, and it's pretty much predictable. Second one is a bit more difficult. This is what goes wrong along the road. So if you have problems along the road, for example, a gearbox that breaks down, blades that start to deteriorate, it will cost you a lot of money to replace it. You can predict it more or less, you can make an estimate, but you're never sure. If you buy a turbine, you can say, okay, I will replace the gearbox 2 times or 1 time. You don't know. So there's a lot of uncertainty there. So there's a lot of conservatism in the business plan. There's a lot of money set away. So there's large margin in improvement here. Another thing is cost reduction by more optimized operation and maintenance. So if you are smart on how you manage the asset, how you use it, if you can do early fault detection, you can do an optimized logistics approach, and you can avoid subsequent damages, you can drastically reduce the cost that you will acquire or that you will have during the lifetime. That's what I want to talk about. So maintenance strategy as such consists of three main things. Everything is possible. First thing is the system complexity. We have a very complex system. The bigger your turbine is, the shorter it has been on the market, the more complexity there is, because there's less known about this type of machine, so there's more uncertainty, more complexity. Then the allowed risk or the guaranteed uptime. The business plan of most of the developers is the same. They will invest in the farm, and they will make a deal with the OEM to have an uptime agreement. So they will make a deal, okay, 95% of the time the turbines will be available and producing. You can do different schemes. You can say, okay, when there is wind, they need to be available, or it depends on how you write the contract. But this allowed risk level, or the guaranteed uptime, is important, because the tighter you put this, the more investment you need to be able to realize this. And I will show this later. And then the money spent. It all has to do with response time, the capability to respond early, and the lead time on parts. If you have a spare gearbox on the shore that is ready all the time, you will be faster in your response than when you have to order it and you don't have a permanent agreement and so on. Having this gearbox is very expensive, of course. There is different ways of reacting. One is reactive. It breaks down and I repair it. This will mean that you will have quite some downtime. Preventive. I know that certain things go wrong, so I will repair them in advance. This can be either time-based or hours of operation-based. And predictive, where you try to assess what is the current condition of the component and act based on this. You don't use one of them, you use all of them. You just decide on, for the specific components, I will use predictive for this one, reactive for the other one, preventive for this one. It all depends on how fast you can respond and how complex the failure is. Traditional O&M vessel just goes from the shore to the farm, transports the crew and their material, stays there while they work, and come back. For one of the farms we work with, for example, it means that the vessel goes 2 hours and comes back 2 hours. So half of the day is lost just by going back and forth. The further you go in sea, the more troublesome this becomes. So what they then do is they put a support vessel. So you get a vessel that has crew on board and that will do the maintenance from this vessel. They can pretty much do everything. They have spare parts and so on, and they're very well organized. This is very expensive, of course, because you need the vessel, the crew, the parts, and so on. But if you want very high uptime, this is how you do it. You can also do helicopter intervention. The guy can take one box, not too much. It's for when a switch is broken or something small. But when there is high waves, but the wind is still low enough such that the helicopter can get there. The bigger your turbine is, the more likely you are using this for small issues that are costing a lot of money and are easily solved. Waves is very difficult, especially in the North Sea. There is periods that you just cannot access the turbine. So it can be weeks that you cannot access it due to the high waves. This means that if you have a component that is broken, we've seen this, it can take 3 months before it's replaced due to lead time and due to weather conditions. Especially for large ones. For large ones, you need these things again, the very expensive ones. They can operate in a certain weather window, but they cannot operate when it's very high wind condition, when it's very high wave condition, such that finding the right moment is already a challenge. So basically what you want is, if they come along, because you will have breakdown anyhow, that they can do more than one job, and that you can know in advance when roughly you need them such that you can negotiate a good price. So predictability is important there. And then the last part in the matrix is yield optimization. So you have cost control during the lifetime, and you want to make sure that your turbine is doing what it should do. You have a warranty curve, so the power curve that I introduced before, and you have reality. And what you try to do is keep track on how the turbine is, how it's behaving, and how close this is to what was promised. I have a nice example here. It's real data. This is a down-rated period, such that the turbine is only producing at 33% of its nominal power, although there is enough power in the wind. I touch upon this because later I will use it again. But you can easily see this in this power curve fitting or power curve analysis. So my whole talk up till now came down to one thing: risk and the probability of failure. You want to have control on what will happen, and you want to know what is the risk that something will happen that I didn't anticipate. So probability of failure, actually that's a design criterion. In the design, everything you design, and it's in all industries the same, you will design with a certain certainty. You will say, okay, if I make it this strong, I know that in 99.999 cases it won't break. So you have a certain risk. 20 years with a turbine is a long time. There is, especially for rotating components that are highly susceptible to load variation, it's a bit of a challenge. Again, I move to the Gearbox Reliability Collaborative. This is reality. So theoretically, you design for the bathtub tub curve, sorry. So you have failure in the beginning, the children's diseases, and then it gets stable, and towards the end of its lifetime, you start having issues again. That's what you expect. You can calculate for this, you can predict it, your maintenance strategy can be optimized for this. Thing is, in reality, we see that there is premature failure. There is certain things going wrong when the curve should be flat. What we actually want is this. If you want to reduce the cost of wind, you want to be able to use it longer than its original 20 years. You want to refurbish some stuff, put in new bearings in the gearbox, new bearings on the blades, certain things, so that you know, okay, I'm good to go for 5 more years, because that's really bringing in money. You already have the asset, it's there, and by making some tweaks, you can use it longer. So actually what you want is deeper understanding of what is critical, what goes wrong, and you want to minimize your risk. Actually, that's a design optimization. You want to understand what are the degradation mechanisms that are happening, so the physics of failure. Once you know what they are, you want to consolidate them, bring them in the design standards such that the new designs won't have trouble with these kind of failures, and base design really on lessons learned. It actually all starts with loads. In the beginning of your project, as I discussed, you assess the loads, and the loads are actually the starting point of everything. In the standard, you have the definition of different load cases. They comprise of wind load, wave load, and electricity-induced load. I will show an example there later. And based on these loads, you calculate the strength of all components. You will make a design, again, go through the loop, see whether it's improved, and so on until you're satisfied. So it all starts from the loads. Of course, you need to be sure that these loads are the real loads, otherwise you design for something that is not the real thing, and you could experience failure. Other challenges, it's a multi-physical problem. You're not just looking into one discipline. It's a combination of aerodynamics, structure, machine building, electrical engineering, and so on. And the machine is also responding as a whole. And I have a nice example there. We did a measurement of a turbine. It's not this one, but it's another one, where the wind is exciting the system. And I'm using a sensor that is on the gearbox. So I'm not measuring anything in the tower to estimate the tower resonances. So each structure has a resonance. At this frequency, it responds very violently. And basically, I want to estimate what happens in the tower based on a sensor that's not even close to the tower, to show you that it's really all interconnected. So you really need to look at the turbine as one whole thing and not a collection of different subcomponents. That's also part of what went wrong in the past, where people were looking at the gearbox, the generator, and so on, but never at a real complete picture. Then the design optimization. You need to know what goes wrong. I took input there from an FP7, a European project, Reliawind, where they are looking at failure rates based on field data for turbines. The Gearbox is one. It's a project already that's from the past, so it's already old. But one of the components that has big lead time is the gearbox. We still see it today. If it goes wrong, you need to order it. You need to have this jackup vessel to take it out. So it costs you quite a lot of money. So it's a nice example to illustrate what monitoring can do and how you can use knowledge about the future to be smart about this. So again, we move back to the GRC. About 40% of the US fleet is documented in this Gearbox failure database. I showed it before. It's one of the subtopics that GRC is working on. And they're really documenting when things go wrong in the field. Because then you can draw statistics and you can learn generically from across gearbox manufacturers what tends to go wrong. So where is there still room for improvement, or where is there possibility that something is missed? Bearings is 64%. I will have an animation of a bearing later on to show you what it's exactly. So, and it's predominantly in the high-speed stage. So the last stage of the gearbox, that's really at high speed, those bearings are the most susceptible. I will focus on them, and I will also focus on planet carrier bearings. So bearings in the front of the gearbox. Why is that? If they break, the whole gearbox needs to be replaced. So it's one of the things that costs quite a lot of money. One of the examples in this is actual cracking. I'm not the expert on this, but there is research going on. The interesting thing is today there is no consensus on this failure mechanism. There is different hypotheses about why it's going wrong. There is discussion about amongst researchers, different bearing manufacturers, but today there is no consensus on the failure mechanism works this and this and this way. There is certain factors that are that have shown to be influential. If you want to learn more on this, Aaron Greco is the reference from Argonne Lab. He is one of the researchers who is the furthest along in this field. He's also part of the GRC. So up to today, it's not fully understood what goes wrong, but we know that dynamic loads and dynamic load variation is one of the drivers. It's not the only driver, but it's one of the drivers. So it made us thinking, okay, can we do something with this? So we did a test on the dyno. So it's what you see here is complete nacelle inside. So it's in the lab. We can apply 6 degrees of freedom loading at the front. So basically all the rotor loads can be introduced. And we have a microgrid, so we can simulate the electricity grid as well and do dynamic events. The component we are looking at is the high-speed bearing, so the one that is very susceptible to failure. And basically what a bearing does is you have a shaft in the middle and then rollers in the case, this is with balls, but in the case of turbines you have rollers that allow the shaft to rotate in a fixed frame of reference. So the housing is fixed, the outside ring is fixed, and the shaft can rotate. The rolls will facilitate this, so they will roll along, and they will do this without sliding. Theoretically, they will have no slip. The problem is, if you go for very high RPMs or higher RPMs at low torque, the preload on these rollers can be not sufficient enough, and they can start sliding instead of rolling, which means that you get degradation of the oil film, which means you can get metal-to-metal contact and failure and initiation of cracks and so on. So what we wanted to know was, can we introduce this, so it's a mechanical degradation, using an electric excitation? And this comes back to the events that were also mentioned by Aaron in the framework of WEC. And the event we choose is a grid loss. So you can imagine the turbine is spinning, and I just unplug it. So the power goes from full load to nothing. It cannot produce electricity anymore. So all of this energy needs to go somewhere. So you can compare this to a spring that's completely turned and has a lot of force in there that you just release. So what the gearbox does is, this is the RPM. We didn't brake. Turbine will normally brake, but we really wanted to understand what happens with this non-torque loading, so with this torque reversal. So here you have the torque signal, which starts bumping up and down. So you have positive torque, negative torque, positive torque, negative torque, and so on, while you are at high RPM. So you can imagine the rollers that are in the bearing need to go one side, then they are unloaded, the force goes in the other way, force goes again in the other way. So you get very strange behavior. And what we see is, we measure with strain gauges in the teeth of the gears. We see that while they are rotating, they start slamming. So one side, the other side, one side, the other side, but it's continuously happening while they are rotating. The frequency of slamming is driven by the resonance of the drivetrain. So it's a resonance phenomena that you can predict because you can estimate the resonance. And it's really, this slamming is really impacting the teeth. That's still okay, they are very strong. But we also see strange behavior in the bearing. We see that the rollers start to slide, which is something that, slip is something you don't want. There's a lot of research that says that slip is an important player in failure mechanisms, and we've shown that you can really get this going by having an electric excitation. So electrics can introduce mechanical degradation, which again underlines this multiphysics of the problem, which makes it very interesting but also very difficult to tackle. So what are we actually looking for? I want to minimize risk. I want to optimize design. So I want to have cost control. Actually, I'm looking for understanding. I want to learn about what is happening to this asset in the field. And I want to know, is it the same at each site, or are there differences between the sites? And is every turbine in a farm just as old? Or are there turbulent effects or other things happening that make that some of them are older than other ones? Because I need to know it in my strategy how to use it. Actually, this is all about understanding. We know that the marketing people are trying to do this. They want to divide people in certain categories to predict what they will be doing. They want to understand their assets' behavior. There's whole industries built around this, where they try to predict what you will do, try to market certain products towards you, and it's based on understanding your behavior. That's actually what we want to do. It's time for wind. We want to understand each turbine, how it's behaving, which ones are alike, and how they will respond in the future. How does this relate to OPEX reduction? The first thing is you can repair upon failure, traditional alarm. We want to go one step further. We want to go to an advanced alarm where we try to detect what is the initiation moment of failure, because that will give you a lot of information about what was happening at the time. So what was really happening that introduced this failure, for example, the grid loss. We want to have a propagation ID. So we want to know how fast is it propagating, because we can take action. I've shown you the turbine that was derated, so you can produce less energy, but you're still online. And you can use it to survive a period of bad weather before a repair, or to survive a period in which you order the boat or you order the gearbox to do the repair while you are still producing and your asset is not degrading too much. And the real interesting thing is if you have load history, because then you can do this. You can do field data enabled design. You can do a failure mode effect and criticality analysis. In this, you can analyze what went wrong, how did it go wrong, and how critical was it. So you can really take action there. And actually, it all comes down to this. I need to know what is the current condition and what is the usage history. What is important here are the events, and that's what I will focus on, and those are the ones I really want to get out. Turbines do not fail generally due to high cycle fatigue in this premature phase. So the curve you saw that was going up in the, after a few years, it's not the traditional fatigue that is causing this. It's not the stuff that's in the standard. There's other things happening that we don't completely understand yet. Events are important. I want to go to if-then scenarios. If this and this and this has happened and I saw this, then it will probably do this, where I have event and load history for lifetime assessment. There's a very nice thing going on that is starting now, a new era, the industrial Internet of Things. It means that there is a lot more sensors embedded in all kind of machinery, because we don't do this just for wind, we also do it for compressors and other machines. And it means that you will have more insights in what is happening. You have more access to data. So how do we want to use this? We want to get to predictability, learning on the fleet level. Again, I have a PowerPoint crash, but it's not so bad.
You need to collect data on your Apple.
Yeah, it's my PowerPoint has issues apparently. Okay. So we were here, the Internet of Things. So I want to learn on the fleet level. Again, I will take the bearing example to illustrate my points, because it's important. It's one of the most critical components in the whole system. And we have quite some nice cases that are real life that I can show you that underline this. So first things first, what data do you have? You have time series data, so sensor data that you collect. And you have status logs. Status log is whatever the turbine is doing, it's logging it. For example, if it doesn't start up, it will put a message, I started at this moment in time. If there is an alarm going off, it will record this, okay, alarm X at time X, and so on. So this information is important to get in. We will then start building our approach. I will first talk about our scalable data storage. Then multi-level learning, decision support, you want to come to a decision, and visualization. The first thing is integrated storage. We have a nice opportunity. We are connected live to the farms. So we have 128 turbines where the data is coming in live, and we needed to do something with this. So we've built a platform, a scalable database, that is able to take this information, store it, and make it accessible for automated analytics programs. So it means that if you program a metric or you program a certain tool, it can run automatically on the data and it can do it live. The data that we collect is SCADA data, 10 minutes data. This is about 400 parameters in the turbine. It's sensors like temperature, pressure, and so on, stuff that's not evolving too fast, such that this 10-minute data is sufficient. That's where it stops in most turbines. We have the advantage that we work together with OEM, so we also have access to the controller data. So we sample the operational data of the controller at higher frequency. This gives us the advantage that we can look into the events that it's doing. For example, the startup, we can really track this. We also have the status codes. We have maintenance data, again, coming from the OEM. This is important because we want to know cause and effect. So you also need to know what was changed at which moment and what was really happening. Condition monitoring data. This is accelerometer data. It's very high frequency, which I touch on later. Particle count. So in the gearbox, there's a sensor that measures if there is metal particles coming in the oil, which gives you also an idea about degradation. We get that too. And then dedicated measurements. We have our own measurement equipment that we've installed on several turbines where we get very high frequency data, and that's also used. Then you have this data, you need to do something with it, because otherwise it's just standing there and doing nothing. So you want to learn. If you want to learn, you want to do it in a structurized way. The first thing we look at is the current condition. It's like for your patient, how is his pulse? How is he doing? Is it normal? Is it abnormal? You can already deduct quite a lot from this. So I start by looking at one turbine. The things I will show are in parallel, so we do it for a lot of them, but it makes no sense to have the same graph 1,000 times, just look at one. So we start from this sensor data and status logs. The first thing we do is very advanced vibration analysis. In this vibration analysis, we combine machine learning with signal processing. So I start from here, an accelerometer signal. So I measure the acceleration on the gearbox at 15,000 hertz. And I will do very advanced signal processing on it first. So I will try to embed physical knowledge that we have about the system to already extract information from it. On top of this, I will go in detail how this works in the next slide. On top of this, I do a kind of classification where I take the operating conditions and I filter them out, such that I can make different periods in time comparable to each other, and I can track what the asset is doing. And from this, I extract a feature about the health linked to the gearbox, and for example, the first planetary stage measured on this sensor. I will do this for all sensors, which will give me different features. So I will get insights in system condition. I will go a bit deeper into the block. So what is this physics-based signal processing? I again have here my animation, so the bearing. You can see that it's spinning around. When you know the speed of the shaft, you also know how fast these rolls are moving, and this gives you information about what their current condition is. If I, for example, so this is the load zone, by the way. So your shaft is pushing, and at that zone you have high load. The other one is not loaded too much. I will use this later. So if I, for example, have a crack in the outer ring, what will happen? The rolls will pass by. You will see the crack, so you have this impulse, tack, tack, next roll, tack, tack, and so on. Because you are in the load zone, the force here doesn't change. The rolls are pushed onto this crack all with the same force, so they will give a similar response. That's what you see here. So you have this impact, 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 and so on, and the amplitude is always the same. This will give you a very distinct frequency signature. You can, by looking at the frequency signature of the accelerometer, you can say, okay, it's that bearing, the outer ring, where there is an issue, by the height of the peak and by the frequency of the peak. If I, on the other hand, have a crack on the inner ring, you will see that the inner ring, the crack will rotate, so the shaft rotates, so the crack will also rotate. So it will go in and out of the load zone. And you can see it in its response. Again, you get this tuck, 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 so you have this impact, but the impact gets smaller, harder, depending on whether or not it's in the load zone. So this again gives you a very distinct frequency signature. You have a frequency and you have sidebands. The sidebands are related to this going up and down of the force, sorry. And again, you can extract this. If you look at the spectrum of the acceleration, you can say, okay, I see this peak, it's linked to this bearing in a ring, so there's a problem there. So it gives you very detailed information about where you have an issue, and you get a very distinct signature for it. Then the last one is a ball defect, or a roller defect, where you have a lot of impacts because the roll will continuously rotate, and again, you get this going up and down due to the fact that you go in and out of the load zone. And again, you get a very distinct signature. This is perfect, works fantastically. There's only one problem. What I'm showing you now is on a test trick. So if you have the sensor placed on the bearing and there's nothing else happening around it, then you get this. This is what we want. But if you want to use this in the field on a real gearbox with 15 shafts, 10 bearings, and the wind continuously changing speed, you need to do some other more intelligent things than just this. So what we do? First thing is we take away the speed variation. Turbine will operate at constant speed, but it's not constant. You can see it here. It still goes up and down because the control it has is it's moving its blades and it's controlling the torque, but still you have 0.1 RPM at the front that's going up and down, which means that your peaks are not peaks, but mountains. They get smeared. So this is a real spectrum, real gearbox, and you can see that I don't get these perfectly nice peaks. I get these mountains of frequency content. So the first thing we do is we go to the angular domain. We try to take away this speed fluctuation by, instead of sampling at constant time, we sample at constant angle. If you do this, you move to this spectrum. It's already a lot cleaner. The peaks are very distinct, so it's very interesting. Then you bump into another problem. The peaks you see here have nothing to do with bearings. It's gears. The gear, it's logical. The teeth are constantly touching each other, so it gives quite a lot of energy, so a lot of excitation in the frequency spectrum. So what I'm actually interested in is here, in this noise thing, and not this. So I need to filter this off in order to go to an automated processing. We use a thing called Capstrom for this. And then what you get in the end is this. This is the BPFO, so the ball pass frequency outer ring, ball pass frequency inner ring. So that's what I showed before on the dyno, those characteristic frequency signatures, they start popping out after all of this cleaning, and you can really look at what is happening. I have an example here. It's a real case again. The black case, there is no BPFO, so the frequency is, the amplitude is 0. After failure, so after some time with failure initiation, the BPFO is huge. So based on this frequency signature, I can tell you it's in this bearing, the outer ring has an issue, but it's after all of this cleaning. So once you have this, you have a feature that you can put into a machine learning model. Your machine learning model can compensate for all of the other stuff that's going on, and you can extract a feature. That's step one. So it's the first thing, vibration-based analysis methods, but we can do it under different operating conditions, and we can do it for different cases. Then there's a lot of learning going on slower data. So on the 10-minute values, for example, at temperature, you can model its normal behavior. So you take historical data of a whole set of parameters, for example, the RPM, the power, and so on. You can predict based on the other parameters what will the temperature be. You can learn this with machine learning techniques, and then compare the real temperature to the predicted one. This allows you to see when the temperature starts going up or when it starts behaving very strangely under different operating conditions. We use this as an alarm metric, again, as a feature to detect when something is going wrong. You tend to see that a bearing gets heated more and more when it starts to have more metal-to-metal contact or when it starts deteriorating. So it's a very nice metric to detect again that something is wrong. I have an example here. So basically what you get is a expected behavior. You put an upper limit on it, you put a lower limit on it, and then you get the real data. So what I show here is again a real life case. I have 1 year of data. This is a statistical classification to show you that you can see some things going wrong because there were some overheating moments, but not that much. This is the model. So the colored curve is the measured temperature. The range above and below is the alarm range based on the model. And the classification, light green, dark green, orange, red, is based on whether it's within the alarm range, whether it's within 3 sigma, 2 sigma, and so on. And then you can see that we can really see the detection, so the initiation period. This is 1 year, so it's about 7 months in advance. When it started to go wrong, and you can also see that the amount of energy that is in this, so the amount of red energy, so when it's going outside of the alarm range, is growing in time. So it gives you an idea about the propagation of your failure, which is what I needed to get to this predictability. If you can see that this energy is going up. You can use this as a metric to get an idea about, okay, it's getting worse and worse and worse, I need to do something, or I can derate the turbine and try to survive for some time. Okay, so what we do is we bring those two together to get an idea about what is the current condition of our machine, how much alarm is there on the specific bearings, how much alarm is there in general, and this gives you a kind of indicator on how good your system is doing. Then the usage history. For this we do different stuff. One is event detection. Since we have controller data, we know what the turbine has been doing. So when it started, when it stopped, how it started, how fast it did this, and there's value in this. First, I want to show this. The colored graphs here is again real life data from a farm. It's the power that is produced by each turbine, and they're all in the same farm, and yet they're all producing different power. So it doesn't mean that you can just say, okay, one turbine, I look at it, the power is that much, and all of them see the same wind, so they will have the same power. No, it's completely not the case. So you need also in your machine learning approaches individual models for each turbine. What I'm actually looking for is this kind of things, the events. This is wind speed at the top. It's about 25 meters per second, so it's the moment when you have storm conditions where the turbine is pitching out. So it's at a certain moment it says, okay, the forces are too big. I will go turn outside of the wind because I cannot handle it anymore. My design is not for this. There's a certain limit that is defined. And you can see that the turbine is flirting with this. So you get a drop in the wind here. It starts up, and then it sees, the wind is still too high, so it shuts down again. Get a new drop in the wind, it starts up again, and so on and so forth. But it means that you are starting up from 0 to full load, and then stopping very fastly. So it consumes a lot of lifetime. It puts huge stress on your system for actually producing, I don't know what it was here, 2 minutes or 10 minutes of energy. So it's very demanding on the turbine. It's very demanding on the electricity grid because you go from 0 to 3 megawatt and back to 0 in a short period of time. So it means that in the back there needs to be a gas central or something else that covers for this, that you don't get fluctuation that is too high in the electricity grid. So it's something you actually don't really want. So what we are working on is really trying to detect these events, putting them in the load history, and compare turbines to each other, which one has seen more events than the other one, and is this linked to its maintenance history? So do you see more failure for these turbines or not? The status codes are used similarly. They contain the controller information on what the turbine is doing, for example, the startup, the high wind, and so on, and we want to use that in the same way. So we use it here to define the load case. Once you have condition, you know when it starts to give alarms. You are very interested in what was happening at that time. So for example, in this case, we looked at the data, the load, the status log data, and we saw that there were very fast startups in that period. So it could be that they are related. We don't have statistical proof of this. We hope to get it in the future, but we see that these events, which were also linked to WEC, which are linked to most failure, are interesting. We are interested in extracting them from the field data to get these kind of links. If this and this and this happened, then we expect this as well. This brings you to decision support. So bringing the information of condition and load history at the moment of failure initiation together gives you insights in probable links. The more information you have on this, the more probable they become. The more data you have, the more insights you will get, the more statistically relevant your insights will become, so the better you will be able to underpin this. And you can use them for two things. One, to show that there is something going wrong, and also to give design feedback. If you consistently see that certain events are harmful, and you can see this coming from the data, you can also give it as an input to new designs, because it could be that the load cases that they are using are not the ones that are really happening in the field. So it all comes down to connecting the dots. And the biggest difficulty there is that you need an expert. You need someone who has the ability to know everything about a machine, to interpret the alarms, and to connect everything together. These people are very scarce. So what we have in our next steps and what we are really working on right now is a lot of artificial intelligence related research where we try to learn this. So try to learn from the experts and try to improve the algorithms such that you can embed this decision support data in your visualization. And then what we are looking for, what we dream about, let's say, is a kind of dashboard or a virtual control room, actually, because the dashboard is actually less important, a virtual farm that is behaving just like the real one, and where we are showing the operator what to do and learning from him as well. I have another example with alarms, such that you can really embed the expert knowledge into the system, such that you can have all of this knowledge embedded in your decision support, such that if you get certain alarms, the dots are automatically connected, and you can really learn from this and take action for this. So the next step there is control-based on fleet learning. And there I also have an example from the field. What we are actually working towards is not to have fancy dashboards or to show fancy stuff. What we want to have in the end is that turbines can learn from each other, such that they can learn from each other's sensors and can take joint decisions. I will again show the example of the farm under storm conditions. So it's real life data. If the turbines are green, they are not producing energy. If they become red, it means that they've started up. What you will see is that so for the moment at the start, what you see is that everybody believes that they shouldn't produce because the wind is too strong, except for one. He thinks, okay, perfect, I will produce. The wind is not too strong. And he will do it for a period of time, but he will consume quite a lot of its lifetime. It has to do with the fact that he is looking only at his own measurements. He's not able to use the measurements of the other turbines. They're not able to vote on the real conditions, such that he decides on his own, okay, it's good to produce energy. The same for alignment between turbines. What we see is that there is a large variation in the wind speed that they are measuring, and they're all on their own deciding how to align towards the wind and how much wind there is. If they could learn from each other, they could vote on what is happening, they could be a lot smarter, they could be having a lot less trouble than they have today. So here you will see that they are all responding on their own, so you have certain of them starting up, shutting down again, and they do it based on their own information, which in the end, the majority still would suggest not to start up and produce energy for, most of them produce energy for 10, 15 minutes, which in the end doesn't bring too much money, but costs quite a lot of lifetime. And if you are able to do this, the next step then is, if you have the load history, you have the condition of each turbine, you can start using offshore as a conventional power plant. It means that you can act demand-driven. You can say, okay, there is a demand for electricity that is X. I have 5 turbines that have already run during storm conditions that have already consumed quite a lot of lifetime. I won't use those. I will use 5 others in my farm that have had, where the lifetime is still high, where they don't have seen too many events yet, so they will produce. And you really run the show as operator. It's not the wind who does it, like it is now. Now each turbine decides, okay, there's wind, I will produce. It's really the operator that says, prices are nice, I need this amount of energy, my fleet has this and this and this condition, so I decide that this and this turbine will work today. And then you have the perfect balance between performance and reliability. You will have a lot more control on what is happening, and you will have a lot more predictability on how your assets will behave, and hence also a better insight in operation and maintenance. So what I want to conclude with is that there is a necessary reduction in cost for offshore wind. O&M and CAPEX reduction So O&M optimization and capex reduction have big potential. Field data can be an enabler for this. It offers the possibility for faster detection by learning. You can do data-enabled design. It's important to combine different metrics. I didn't go too deep on this, but we see that certain false alarms happen. So the better your metrics are, the more you have, the less you will have these false alarms. And the fleet aspect offers a lot of potential, both with regard to learning as with regard to control. Because if turbines can learn from each other or can use each other's information, they can be a lot smarter in what they do. And thank you for your attention.
Thank you for a very interesting presentation. We have 5 minutes for questions. So floor is open for questions.
Just how much in this whole optimization approach are you learning from other industries?
We are doing the same, for example, for compressors. A lot of our very advanced signal processing techniques, where we also try to track propagation, we are validating on compressors because we have the advantage that you can test them in a lab. You can introduce a failure or initiate a failure, track how it evolves in time. And we try to learn from all industries that we can. But particularly in this IoT environment, there's a lot happening in general with machines. It's not just wind, it's also connected vehicles, it's also production machines and so on. So it's nice to see that they're all moving into this direction.
How many features do you have to keep track of, and how much data actually do you have to store, and how far back do you have to go in time? Do you have to keep data for years, or you don't need to go too far back? What sort of magnitude of storage that you would need for an offshore wind farm?
What we do now is, because it's research, we keep everything. So we have 4 years of data for the 10-minute values. We have 1.5 years for the 1-second values, and we have about 4 years of data for the accelerations. So we have terabytes of data. For a lot of the metrics, it's nice to have at least 1 year. Because you have I didn't touch upon this as well, but there's a clear seasonal effect. So we can see in all of the temperatures, for example, in the bearings, we can see that it's summer or winter time. And if you want, you can take this into your model, but if you want to have clear training and so on, it's nice to have it for a long period of time. The same for vibration data. It's good to have a healthy period. That's the most important part, to have a very good healthy period, because that will help in getting the detection better. We also try to do it for each machine, try to find a good healthy period. We also have metrics for that, such that, because every machine is different, we've learned. So it's difficult to answer how many features you need. For every bearing, we have at least 4 to 5 features. But for the moment,
just about the gearbox. But if you add more sensors on the blades
I think you will go into the thousands, because but it's not so bad as long as you can do everything automatic. It's better to have more features and do some kind of voting than an ensemble of models than to have fewer.
Well, 1,000 isn't too much. I mean, the medical community is using tens of thousands of features for their disease detection.
Yeah, but it depends on how far you want to go. For vibration, for example, we can have 400 or 500 easily, but we try to combine and try to find. We have the advantage that stuff tends to go wrong, so you can learn from this. You can see what is a good one, what is not so good, to detect certain things. But it's continuously learning. We are moving one step at a time, so we still have quite a lot to learn on this.
What kind of kernels do you use in your machine learning algorithms?
For example, logistic regression, the clustering classification, neural network, those kind of things. But we try to not just fit the model. We always try to understand more or less the parameters that go in, that they also make sense. From the physical side, for example, a bearing, the temperature of a bearing will always be linked to the power that the turbine is producing. So we try to also understand the parameters that go in, and then okay, you get the black box, but then at least you have some feeling about what is going on.
With the acceleration data and the high frequency data, are you storing that as time series data at this point? And then, so you can try different post-processing, or are you going to the frequency spectrum right away and tossing?
No, we have the time data.
For more commercial implementation, once you get a handle on it, would you visualize just doing the physics modeling real time and then just taking the results of that?
Yeah, but there is also, even in that part, there is, we're not there yet, let's say, to throw away that data. I would somehow try to either store it locally, but that at least you can learn from it. We have one of the biggest challenges that today, most of the commercial systems measure once a day, 10 seconds, and you have completely no idea about, for propagation purposes and so on, it's very difficult.
Sure.
And we have measurement campaign where we did it for a long period of time, where we store the data, and you can get a lot more insights in, for example, during a startup, you can see that certain peaks are growing, et cetera, et cetera. And that's, so even I would try to store it somehow, that if you have certain cases where you see a certain failure, you can go back. It's very frustrating. We had an enormous amount of time. You see something go wrong, and then you get the data, and it's very few data. And you say, okay, if I had this and this and this, I could do that. No, it doesn't work. If I had this and this and this, I could do that. So I'm very reluctant to throw away data.
That's a really good insight.
You may have covered this very close to the beginning, but when you install this sort of sensorization, does the wind farm approach the people that are doing this, or is it government mandated, or is it done in a specific facility? Like, how does that work?
We try to sample everything that's in the machine, such that we already have that, and we also install it ourselves. So we have our own instrumentation package.
I mean, more like, is it as far as the businesses themselves? So does the farm approach you, or are you approaching the farms? Like, how does it work on a business level?
We do this on a research level, so it's in that sense, the farm is a partner,
Okay.
and we get access to the facility, and they try to facilitate us being able to do the research there.
I've noticed that at the beginning of the slides, you said that the high cycle fatigue is not important. So I noticed that there is a lot of high frequency phenomena. So how do you get that conclusion?
High cycle fatigue is very important because it drives the degradation of the system. So that's it's very important. The only thing is, for the failures that are not explainable today, they are not explained by this high cycle fatigue. So there must be something else that is happening, that is loading the system in a way that is not ideal, that can initiate this kind of failure. So yes, high cycle fatigue is extremely important because it drives the lifetime of all structural components. It's also, for the rotating components, very important, but it doesn't cover everything. Otherwise, we wouldn't see the failures that we see now.
So there are some other factors.
Yeah, and that's also what we are trying to find. For the structure itself, if you have the loads, you can do a rainflow counting, and you can see, compared to the design, how much there is already consumed, so you can get an idea about the lifetime. For rotating components, it's a lot more difficult. You have this too, and it already gives you insights, but you also need to know the more dynamic stuff that the machine saw, because it will also be important with regard to these non-fully explained failure phenomena.
So for the tracking system you are running right now, it's like, how long do you need to find out like a figure, or it's like how what's the time magnitude you are costing for your whole signal, for whole data processing system? It's like it's like right now, a failure occurs in the machine. It's like how long can you find that?
You try to find it. The data is live. Up till now we've worked quite a lot on historical data. We're trying to do it on live data now as well. And basically your model detects it instantly whether or not it's normal or abnormal. So you get this information feedback as fast as you get the data.
Yeah, and I assume it takes time for your system to learn from the features and you.
Yeah, of course.
Right.
But for most of the SCADA stuff, you have historical data because it's always stored, so you can learn from the historical data. For the physics-based things, you can learn from the physics. You need to know the frequencies, so you can also start instantaneously. So I don't expect there will be a huge time to start with this, at least to get something online.